Hello, good morning, good evening, good afternoon, wherever you may be tuning in from. Welcome back to Quantum.Tech, our third and final day, and we have a spectacular lineup for you today. To kick off today, I'm delighted to welcome back Jon Allcock. Jon is a senior researcher in the TENCENT Quantum Laboratory, where he works on investigating practical applications of quantum computing for machine learning, material design, and chemistry. We had the pleasure of hosting Jon 18 months ago at our physical conference in Boston, and you're set for an excellent presentation. Jon, the floor is yours.
Thank you very much, Amit. It's really a pleasure to speak at this great event. I'm joined here today by my colleagues Kim Xie and Xiaogang Hao, who've led the development of a lot of the things we'll be talking about today. And they'll be sticking around till the end to answer any questions you might have. At the TENCENT Quantum Lab, we are very interested in advanced computational techniques, that's machine learning, cloud computation, and quantum computing for pharmaceutical and material science research. And we've been working hard with our partners from universities and industry to develop tools and also understand how these methods can be applied to the industrial and academic workflows. And today we'd like to share just a few of the things we've been working on in these areas. In particular, an online tool for drug property prediction, a first principles material simulation platform, and also a selection of quantum computing research results for both near and long-term quantum computing as applied to pharma and material science research. So with that, let's take a look at the online tool for drug property prediction. In computer-aided drug discovery, in particularly the lead discovery part of the pipeline, one is typically interested in taking a very large number of molecules and then passing them through successive filtering stages until a fairly small number of candidate molecules can be explored in more depth to see their viability for drug development. And without getting into too many details, in the last few years, a number of these stages of filtering have been the subject of increased machine learning and AI application. And we're also interested in particular in one stage where we are screening molecules for their properties of absorption, distribution, metabolism, excretion, and toxicity. So these ADMET or ADME-tox properties are clearly very important to understand for molecules if we're ever to turn them into drugs that are fit for human use. So we have a new platform we call the ADMET Crystal Ball. It's available or will be available live at this website by the end of the week. And it's a free platform similar to Swiss ADME, GHDDI, or BNN. So if you have any experience with other ADMET prediction platforms, it will seem quite familiar to you. But we've worked hard to try to make it as fast and as accurate as possible by deploying some of our own proprietary graph convolutional neural networks behind the scenes. In terms of interface, it's fairly simple. You input a molecule in the form of a smile string. So that's a sequence of letters and symbols which encode the structure of a molecule. You can also use an inbuilt molecule sketcher or upload the molecule at a number of convenient file formats. And then you just click submit. And within a number of seconds, you'll receive a report with roughly 50 different properties across these ADMET categories. You'll receive some numerical and some color-coded values, and additional information can also be obtained by hovering your mouse over a number of the properties as well to get additional insight into those. In terms of accuracy, our initial internal benchmarking studies have been quite promising. So what you have here is a table of a number of the ADMET properties and the performance of the Crystal Ball platform compared with a number of those other platforms I just mentioned. And in the red, you see the platforms that perform the strongest across a particular indicator. So you can see the Crystal Ball has done quite well. I'd caution not to read too much into this table. This is really some preliminary benchmarking work, and it's also on a fairly limited number of the categories. But the real key takeaway is that this is very much under active development, and we really welcome collaborations from anyone who's working in this field or is interested in this area to try to help us further develop the platform and make it as useful in practice as possible. So moving on from property prediction of for the drug discovery pipeline, I talk a little bit now about first principles material simulation. This is where one attempts to model the properties of a material using only the laws of quantum mechanics as the prior assumptions. And this is very widely used in computational material science, condensed matter physics, and quantum chemistry. And typically, one inputs a molecular structure into a supercomputer, runs some fairly expensive computations, and then obtains the properties out the other side. And while this works well, the traditional reliance on supercomputers can be costly, and also they have issues with accessibility. For instance, one may not have a supercomputer available to you, and there may also be a learning curve in doing so, and the interface may not be that user-friendly. These supercomputer platforms are also inflexible from a resource allocation perspective, in that you can't necessarily just pay for the resources you need on demand. And so what we're trying to do is create a platform which replaces the supercomputer infrastructure with a cloud solution to address these issues and improve the user experience from end to end. And we call this the TENCENT Elastic First Principles Simulation, or TEFS platform. You can find details about it on this website here. And this is really our attempt at making a flexible and scalable and affordable platform. There are no charges for TEFS itself beyond the cloud fees you pay for allocating the resources you need to perform the computations. And the cloud elastic model means that resources are really paid for on demand. Beyond that, we've worked hard to try to make this tool as useful as possible for real practitioners. So we've built in some data visualization functionality, and also some tools to make this useful for collaboration and collaborative work. So if you're working in a research group in a university or a corporate research department, we hope some of these features will be useful to you. In terms of the backend, TEFS uses the popular Vienna ab initio simulation package as its backend, and so users do need their own VASP license to run the platform. We're currently in beta stage, and we're aiming for a China release fairly soon, in early part of the second half of this year, with an international version to follow. The Chinese version will make use of the QQ or WeChat social media platforms for registering and logging in. But when the international version comes live, then email registration and login will also be available. In terms of user experience, if you've ever worked with VASP before, it should seem fairly straightforward. The process involves uploading some standard input files which encode the molecular structure. Or you can compose these files in an inbuilt editor we have in the platform, and provide a number of templates to make it very easy to modify and adapt these files to your needs. But once you've uploaded these input files, you simply click Run the Experiment, and after some time, you will obtain the simulation results, which in visual form give you access to the relaxed crystal structure, electronic band structure, density of states, and so on. And all of this data can be scaled and cropped and rotated as needed. And so it makes it very easy to take the output of this program and feed it downstream into your workflow. In terms of upcoming features, I mentioned some collaborative tools. So we're planning to incorporate a kind of joint paper editing feature. You can think of this as a kind of overleaf functionality for writing papers collaboratively, and also some online platform for discussing results directly through the platform. We also want to cater to some power users by allowing for batch submissions of jobs, and also some advanced data analysis that can be run through a command line interface. So if you are interested in trying to run some large-scale material simulations, and you want to find out a bit more, then please reach out to us at this website at tefscloud@tencent.com. So the ADMET and the TEFS platforms are addressing needs of today, but we're also very interested in understanding how quantum computing can be applied to material and pharma research in the future. And to this end, we've been trying to understand both the practicalities of how to get the best out of near-term devices, as well as understanding the capabilities of fault-tolerant quantum computers when they do become available. So for instance, we've been looking at how to design and construct good ansatz for near-term variational algorithms. We've been looking at how to optimize annealing schedules for using things like the D-Wave device. We've been asking about whether near-term devices can solve problems like modeling energy transfer in systems, and also how one can accurately characterize noise in real quantum devices so that algorithms can be optimized to run on the hardware we have available now or in the near future. In terms of long-term fault-tolerant quantum computing, we're asking things like how quantum computers can be used to solve graph-based problems, which appear very ubiquitously, and also whether quantum computers can help with some machine learning problems, in particular classification. So I won't have time to go through all of these here, but I hope to give you a selection of some of these results. And then if you're interested, you can take a look at the references on this page. So in terms of optimizing near-term variational algorithms, the variational quantum algorithm framework is a very flexible framework for trying to solve problems on near-term devices. And the basic idea is to have a quantum circuit consisting of a number of tunable gates. And this quantum circuit is then embedded inside a classical feedback loop. And by running this feedback loop, you can try to find the optimal parameters to solve a problem of interest. And while this framework is fairly flexible, in the sort of standard formulation, the actual structure of the circuit, which we call the ansatz, is typically fixed, and it's only the parameters that one attempts to tune. And this raises the question of how to design a good ansatz that not only gives a good solution to the problem you're looking to solve, but also has other desirable properties like noise resilience or compatibility with hardware connectivity and so on. So this can be kind of viewed as a neural network or quantum neural network architectural design problem. And this problem also appears in classical neural network design. And a recent result called differentiable architecture search has been proposed, which gives a systematic way of designing neural network structure. And so we're interested to see whether something similar can be done for quantum neural networks. So we call this differentiable quantum architecture search. And the idea is to construct a quantum circuit that initially consists of a number of empty slots. And then you have a pool of operators that are each tunable. And the idea is to optimize both which operators fill which slot, as well as the values that each of the operators takes, the values of the parameters that each of the operators take. And we find that this framework gives some quite interesting applications. For instance, when trying to solve a combinatorial optimization problem, one option is to use something like the quantum approximate optimization algorithm. But we find we can get results equal or better than using the QAOA ansatz, but with an ansatz that uses fewer gates than in the standard formulation. And we also find it has a nice use in terms of generating noise resilient circuits, especially useful for near-term devices. So for instance, if you look at the bottom left, this is a quantum circuit to perform the quantum Fourier transform. It's a very sort of useful circuit primitive. And this circuit is a textbook circuit, which should work well on a noiseless device. But when run on a noisy device, you see that the fidelity, or rather the accuracy of the circuit is somewhat low. But we use the DCAS framework to insert additional slots into this circuit. And then by optimizing the gates and the values of the parameters in those slots, we can create what looks like a more complicated circuit, but one that actually performs the Fourier transform with a higher fidelity than in the first case. And so we think this idea about trying to get noise resilience built into algorithms should hopefully be useful for the near-term devices that we're expecting to see in the next few years. Beyond the quantum circuit model, quantum annealers are also a subject of great interest these days. And in quantum annealing, one typically takes a two-step approach to solving problems. You first start off by initializing your system in the ground state of some easy to prepare Hamiltonian. And then you gradually change the Hamiltonian to a target Hamiltonian that encodes the solution of a problem you're interested in. And the trick is that you want to make this change, perform this change slowly to keep the system in its ground state, But you don't want it to occur too slowly because you want the algorithm to be quick, and you also don't want too much time to pass for noise and decoherence to take effect. And so what you're interested in is what is the optimal way to interpolate between these two Hamiltonians, and this becomes a scheduling problem. So you can ask what is the optimal schedule, the optimal way to vary from one Hamiltonian to the other. And many possible schedules are possible. So you can, for instance, have a linear schedule where this tunable parameter S, this interpolation parameter, varies linearly with time. But also you can consider more complex annealing schedules. And trying to find the optimal one is a non-trivial task. So our approach to this is to use something called Monte Carlo tree search, which is a powerful classical reinforcement learning technique for searching large spaces. And the idea is to try to apply this to the annealing schedule problem by expressing the schedule as a Fourier series with these coefficients x in red, which are to be optimized over. Or rather, we can search over a very large space of possible values of x and try to find the best one. And the way the Monte Carlo tree search works is you explore a number of different values of these parameters, and then you pass the corresponding annealing schedule to a quantum annealer to actually perform the experiment and get some feedback to see how well it performs. And based on this feedback, the MCTS algorithm then decides how to adapt the parameters in the next step. And it tries to strike a balance between exploiting values that it historically has found to work well versus also exploring some previously untested values. And this method can be combined with neural networks for some improved efficiency. And in fact, this Monte Carlo tree search plus neural network combination is more or less at the heart of the DeepMind AlphaZero algorithm, which is also one of the inspirations for us to try to find its uses in quantum annealing optimization. So we tested how well this works, and the results are quite promising so far. So this is the result of a combinatorial optimization problem on a number of variables. In the different colors, the blue corresponds to the linear annealing schedule. The green is an alternative method known as stochastic descent, and the red is the Monte Carlo tree search method. And the height of the graph shows the fidelity of the annealer with respect to the true solution. And what you can see then is that the Monte Carlo tree search method rapidly finds better solutions much more efficiently than the linear annealing schedule, and also with much reduced variance, much less variability than the stochastic descent method. So we think this is quite promising, and we're also in the process of trying to explore how to make use of transfer learning so that results optimized for one annealing problem can be transferred to other problems without requiring the entire reinforcement learning algorithm to be run from scratch. And so it's our hope that we can use techniques like this to try to extract even more out of the annealers that are available today. Moving on to modeling energy transfer on near-term devices. This is a very interesting problem. There are quasi-particles known as excitons, which are bound electron-hole pairs. And these are the primary medium of energy transfer in devices like organic LEDs or organic photovoltaics. So modeling this kind of energy transfer is very important, but can be very difficult to do classically. And so you can ask, how well can variational near-term quantum algorithms model these kind of dynamical systems? This is actually a more difficult problem than the sort of ground state or excited state energy estimation problems that typically variational quantum algorithms have been applied to, because not only the ground state, but actually all quantum states are involved in the time evolution, and it is indeed a time-dependent system. But we find that in spite of this difficulty, the algorithms perform well, at least when simulated. So what you see in this graph is the results for a system of 64 organic semiconducting molecules arranged in a three-dimensional lattice. And what we do is we excite an exciton on the central molecule and then measure how this energy dissipates away from the central molecule with time. And two things can be seen from the graph. The first is that the energy dissipates in a fairly non-trivial way. You can see some fairly complex quantum interference effects taking place. And the second is, though, that the VQA results in the dashed red line match the exact results predicted from theory very, very accurately when simulated. When we run the experiment on a real device, we find the noise degrades the results somewhat. So real devices may be still a little bit too noisy for accurate results, but we're in the process of understanding how well error mitigation strategies can be used to help with this. And so we're excited about the possibility of extending the applications of near-term devices to more complex problems like energy transfer in OLEDs. Let's finally move on to a couple of long-term applications. So one thing we've been interested in is understanding how quantum computers can help with graph-based problems. So these are abstractions of things like logistics and transport flow, or social network connections, and so on. And the idea is to have a connection or collection of vertices joined by different edges and try to understand the properties of these graphs. And what we ask is, can quantum computing help us learn properties of complex graphs quickly? And the answer is yes, provided that we can perform or query or graph cuts in superposition. And by this I mean, if you have a graph, you can consider coloring the vertices black and white. And each such coloring constitutes a cut, and you count how many edges are between the white and black vertices. So for these three graphs on the bottom right, these correspond to cuts of size 1, 3, and 2. So the idea is, if you can create quantum states which encode different graph cuts in superposition, and if you can run quantum circuits, or also known as an oracle, which can compute the cuts of each of the corresponding graphs, then a number of properties of graphs can be computed exponentially faster than classically. So for instance, if you're interested in understanding the connected components of a graph, or whether it's acyclic or bipartite, then only logarithmic number of these quantum oracle circuits need to be run in order to solve the problem. And this is an exponential speed up relative to classical. There are a number of caveats with this. In particular, actually implementing such a quantum oracle may be non-trivial and may depend on a particular problem instance. And also one needs to look very carefully at the absolute quantum circuit running time of problems of real interest to understand whether there's a practical advantage here. But this is still fairly early days, and we're excited about the possibilities of finding some very fast speed ups for graph-based problems. And the last thing I want to share with you today is around machine learning classification, in particular support vector machine classification. So this is a supervised learning algorithm whereby one is given a collection of labeled data, say these red and blue dots, and the task is to find a line or a hyperplane that separates these two colors, the data of two colors. And different scenarios are possible. So if it's possible to find a separation in the original input space of the data, this is referred to as a linear support vector machine. But as in the second example you can see here, there's no way that you can separate the data as is given. In this case, typically what one does is map the data to a higher dimensional space, and we call this a feature space, and then perform the classification in this higher dimensional space. And we call this a nonlinear SVM. And classically, there are a lot of algorithms for support vector machines, but in particular, there's one known as SVM-Perf, which is by Jochims from a few years ago, which has very impressive classification accuracy for both linear and nonlinear SVMs. But in terms of its efficiency, it only has guaranteed efficiency in some special cases, for instance, in the linear SVM case, or for some special kinds of feature maps. And so what we've been interested in is whether or not we can use quantum computing to extend the kind of problems that efficient classification can be performed on. And we call this quantum SVM-perf, which is a way of using quantum states, and in particular the amplitudes of quantum states, to encode these feature space vectors and perform the classification that way. And what we find is that we can extend this efficient class of problems to a much wider range of problems than in the original SVM-perf. And so we think this is an interesting idea, that we can look for quantum advantage, not necessarily in terms of speed up, but also in terms of extending the class of problems that are tractable. There are also a number of caveats and things to be careful of when analyzing algorithms of this nature, but nonetheless, we still think it's quite exciting to understand what we might be able to do with fault-tolerant quantum computers when they finally do become available to us. So that's more or less what I wanted to share with you today. If you're interested in any of these topics, in particular, the applications of these things to pharma or material science research, we really would love to hear from you. You can reach out to us for general inquiries at qlab@tencent.com, and specifically for the first principle material simulation platform at the tefscloud@tencent.com email addresses. So with that, I'd like to thank you very much for your attention today. And Lawrence, do we have time for some questions?
Yeah, we've got time for a couple of questions. I'll start with a question from the audience. Jeffrey Cohen asks, "Hi John, are you working with quantum walks and graphs?" Oh, you're on mute, John.
Oh, thank you very much for the question, Jeff. Yeah, quantum walks and graphs is something that we've been looking at. We have some results that I haven't shared with you today, but it's certainly something that we're very interested in.
Great. And a question from Amit. What can we expect in terms of roadmap and highlights over the next 12 to 18 months at Tencent?
So I think the main roadmap is going to focus around developing the platforms we discussed today. The quantum computing research, is a lot of collaborations with partners in universities and academia, and those occur at a more academic pace. We haven't got such strong timelines for those, but I think we're focused on building up the user base and getting feedback for our platforms as soon as possible.
And are you working on quantum hardware?
So quantum hardware is something we've been keeping a very close eye on. It's something we're obviously very interested in. There's been a lot of interesting results and developments, but it's not something that we've got anything to announce at this stage. Just keeping a close eye on it all.
And Karam Al-Gamal has just asked, what quantum simulation frameworks you include, PySCF or others?
So I'm not sure. So PySCF is a popular platform for modeling quantum chemistry, and is certainly possible to use with a lot of Python programming, but it's not something that's embedded in the Elastic First Principles platform. That's based on the VASP, Vienna Ab Initio simulation package software.
Great. I suppose a final question from myself. A lot of discussion yesterday was around talent and resource. How do Tencent resource your talent? Are you looking at people coming over from university? Are you looking at other organizations? How do you get the best people to join your teams?
Kim Shagan, do you want to field this? A lot of the recruitment obviously happens in Shenzhen.
Yeah, maybe Kim, you can go first.
Sure, yeah. So, so basically, we certainly get a lot of application from talented young fellow from universities, like fresh PhDs or someone who just did 1 or 2 years of postdoc. And we also certainly actively recruit a few people that we know who are pretty good in the field. And but just we try all ways to reach out and find the best we could find. Yeah.
Just to add to that, if you are interested in working with us, interning with us, finding out more, then do send an email to the qlab@tencent website email address.
Fantastic. Well, John, thank you for your excellent presentation. What a brilliant way to start the day. Kim, Xiaogang, John, I know it's all very late for you, so I appreciate you staying up for this, and thank you again for the opening keynote of the day. That was great. Cheers, guys.
Thank you very much for having
Thank
us.
you.
Thank you.
It's been a pleasure.
Bye.
All right.